Hello and welcome to our discussion on inferences from two sample proportions. Previously, we've looked at how to find confidence intervals for one proportion, right? You've got one sample and we're doing a confidence interval around p hat. And then we saw how we could conduct a hypothesis test when we had one sample, one set of data, and they were proportional. Now we're going to expand those ideas and look at how we can build confidence intervals and do hypothesis testing when we have two sets of data, right? Two samples and it's both proportional data. And then we'll move on and we'll have a lesson where we do the same thing but with regular data where we're calculating the means of two samples, and we'll look at them when they're independent and dependent, and then we'll move on to standard deviations and variances as well. Okay, so the big difference here is that we are now dealing with data from two populations, right? Two samples. Some examples that we could use these techniques for would be testing the claim that when college students are weighed at the beginning and end of their freshman year, that the differences show a mean weight gain of 15 pounds. This is commonly known as the freshman 15, that people think that freshmen always put on 15 pounds. It's usually because they're living in the dorms and they're eating the fatty, carb-filled food that you find in dorms. And plus they probably are drinking a lot more and getting all those empty calories as well. Another simple claim would be that the proportion of children who contract polio is less for children who were given the Salk vaccine, the polio vaccine, than for children given a placebo. So you're basically testing the effectiveness of that vaccine. And another way that we could use these techniques would be to test the claim that subjects treated with Lipitor have a mean cholesterol level that is lower than the mean cholesterol level of subjects given a placebo. So you can see that this idea of testing two different groups is very common when you're trying to test the effectiveness of a drug, the polio vaccine, Lipitor, and anything else you can think of. Okay, so we're going to have two main ideas in this lesson. We're going to test a claim made about two population proportions, and then we're also going to construct a confidence interval estimate of the difference between those two population proportions. So it's not like we're going to construct two intervals. That would be doing the previous lesson that we've done before on confidence intervals twice. Instead, now we're going to construct a confidence interval based around the difference between the two population proportions. And that'll be the same when we go to two means and two variances. Typical, we have to talk about our syntax, right? What do our symbols mean? The only difference now is because we have two different groups, we're going to have subscripts for everything. So P sub 1, right, P1, is going to represent the proportion from the population from the first population, right? And then N sub 1 is just the size of the sample that comes from the first population. And of course, X sub 1 is the number of successes in that sample, and so on and so on and so on, right? So we're always going to have these sub 1s, and then of course we're going to have all the sub 2s that are going to correspond to the exact same things, but from the second population. Pooling your sample proportion. So this is akin to your p hat, right? This is your proportion of things, but instead of p hat, where it's the proportion of things from one sample, p with a line over it, right? Sometimes called p bar, is just your pooled proportion. It's the total proportion from both populations, because if you recall from the previous slide, x1 and x2 are the number of successes from each of your two samples. Right? So this is how many successes I had in sample 1, how many successes I had in sample 2. So this ends up being total successes, right, across both samples. And then this ends up being total sample size, right? Because it's the size of one plus the size. So that's the total size of all the people sampled. So that's the total number of successes out of the entire group of people sampled. You've now created a p hat, right? A proportion from your sample, but based on both samples put together. So that's your pooled proportion, right? It's like your pooled p hat. You're just pooling everybody together. Requirements, just like all of our other tests, that we have to have proportions that come from two independent simple random samples. So that's very important, that you're sampling independently and they're both simple random samples, right? We always have that simple random sample as a stipulation. And then for each of the two samples, so just like before where we had to have the number of successes and number of failures being at least 5, same thing here, it just has to be for both samples. So nothing really new there, nothing earth-shattering. Okay, your null hypothesis is almost always going to be that your two populations have equal proportions, right? So you'll notice that those are P1 and P2, not P hat, right? We're not talking about what happens in the samples. When we're talking about hypothesis testing, it's always what we assume is happening in the population. So in this case, we're assuming that both populations have an equal proportion of items that have this characteristic that we're testing, right? And then again, because we're dealing with proportions, we're calculating a z-score. And you'll remember, hopefully, the previous z-score was very simply p hat minus p, right? Was the difference between your sample proportion and the proportion of your population divided by the formula that we use basically for the standard deviation of our sample proportions, which was very simply just PQ over N. This whole thing is under the square root, remember? So you can see the similarities between the two. You're still looking at a difference between two things, but instead of comparing one proportion to a population, you're comparing the difference between our two samples compared to the difference between our two populations. But since our null hypothesis is always that these two are the same, this ends up being zero, right? So you're comparing the difference between two proportions compared to zero. So how far is the difference between these two proportions from zero, right? That they're actually different from each other, because if they were zero, they'd be the same. And then down here, we're just doing the pooled P, right? This is pooled P, pooled Q over the first size sample, right? Plus the same thing over the second size sample. So we're basically just doing a standard deviation from those two samples. Now you'll notice that in this case we're using a pooled P, but you may have noticed that in this case where we're doing confidence intervals and margin of error, look at how we're no longer using the pooled P's. Right? We're now using P hat and Q hat from sample 1 and P hat and Q hat from sample 2. And the big difference is, in this case, we're assuming the two populations have equal proportions, right? That's what our null hypothesis was. That's the big assumption, that these two things are equal. And because they're equal, we're allowed to pool our P's, right? We're allowed to use that pooling formula of number of successes from both samples divided by sample size, right? Total sample size, the two samples put together. Because we assume the proportions are the same, we can then pool everything together. When we don't assume the proportions are the same, i.e. when we're just doing confidence intervals, then we're going to use the individual P hat and Q hat from each individual sample. Okay, how do we run these tests? Well, just like before, we can do either p-values or critical values. If we're going to do critical values, you tend to use tables, but you can also get critical values out of technology with some pretty simple workarounds. I still think the p-value method is the best way to go, so you should really get in the habit of using that one the most. So even if they ask you to do a critical value, test it using critical values on a homework question or something like that, feel free to use the p-value method instead, unless of course they ask you what is the critical value, then you have to look it up anyways. So you get what I'm saying, hopefully. Okay. Confidence intervals, just like before, right? We had a simple confidence interval before when we were dealing with our just one sample proportion. And if you don't remember it, I'll put it here for you, where we were estimating the proportion from the population, right? So we just had the P in the middle, not P hat, but P just like here. Here's the P sub 1, so that's the proportion from one population, the proportion from the other population. And then our confidence interval was very simply P hat minus E and P hat plus E. Well, now here's, the difference in my P hats minus E and the difference in my P hats plus E. So you can see the similarities between the two, and of course the similarity for the margin of error before, sigma. The margin of error before, when we had just one population to deal with, it was still this z-score of alpha over 2, and then we had a very similar calculation for our standard error, right, standard deviation, which was p hat q hat all over n. And you can see how this is the same thing, only now we have to take into account both samples. So it's a very similar concept, very similar theory. All the formulas look very similar, and then of course to do it in technology it's also extremely similar and easy. Let's look at a simple example. So do people having different spending habits depending on the type of money they have? So do you spend money differently depending on the kind of money you have? And what they mean here is small bills or change or large bills and things like that. So 89 undergraduates were randomly assigned to two groups and were given a choice of keeping the money or buying gum or mints. The claim, the thing that they're testing, is that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations, and they want to test this claim at the 0.05 significance level. Here's the data they captured. So group 1, subjects who were given $1 bill, obviously a success to them is spending the money, right? That's what they're testing. So they had X1, the number of people who were successes, i.e. they spent the money, and then there were 46 total people in that group. There were 43 people in the other group who just got 4 quarters. Why those two groups are different, who knows? You know, if you had an even number of people, you would probably split them up evenly. But maybe you had some people drop out of the study, things like that. So the groups won't always be the same, and it's good to know that they don't have to be the same. These subjects who were given 4 quarters, 27 of them spent the money. So you can see already, just from the numbers, that it seems that the people with quarters were spending more than the people with a dollar bill. It was more than twice as many for roughly the same sample size. You can, of course, calculate both of your p-hats very simply with success over total, and then you can also calculate your pooled p. Right? Total successes, 12 plus 27 over total sample size of 46 plus 43. So it looks like almost 44% of all of the subjects spent the money, right? Just a little less than 44% of all the subjects spent the money. Check our requirements. The 89 subjects were randomly assigned, so we have that simple random sample. And in the two groups, the people who spent and didn't spend were all over 5, right? I mean, look at this. You've got 12 who spent, 34 who didn't, 27 who spent, and what is that, 16 who didn't. So those are all bigger than 5, so we're good to go there. Okay, so let's start with step 1, right? Remember our steps for doing hypothesis testing. We first need to identify the claim and then write out our null and alternative hypotheses. Since the claim is that money in large denominations is less likely to be spent, we would express that as P1 minus P2. Because P1 was the group that received their money as a dollar, right? And P2 got it as quarters. So the large denomination group should have a smaller proportion of people who spent their money. And if that's our claim, then P1 greater than or equal to P2 is the complement of that. And we would therefore set up our claim here to be the alternative and the null to be strictly equal to, or you could technically make it a greater than or equal to. It's just most people still like the equal as the null. And I tend to think in this instance it is better to leave it as an equals. Now remember, the claim doesn't always have to be the alternative. It's really down to the wording. And because the claim was, less likely, which led to a less than, we know that has to be the alternative because the rule is the null really has to be the equals. Okay, on to step 2. Select your significance level, which was given to us as 0.05. Step 3, determine your sampling distribution. Well, since we're dealing with proportions, we know we're going to be dealing with the normal distribution, right? So we're going to be doing z's. We can go ahead and calculate some of these things like our pooled p and things like that, but this is all just part of step 3 where we determine our sampling distribution and then calculate our test statistics. So these are just leading us up into being able to calculate that test statistic. So here's part 3 continued. We got all of our p-hats and our pooled p's and q's. Remember, q is just 1 minus p, so q bar is just 1 minus p bar, right? It's just the complement of your pooled p. Put all that stuff in. Please pay attention that this 0 comes from this, right? Because we're null hypothesis is that they're the same. And once you do all that, you get a z-score of negative 3.49. So there's your test statistic, right? That's your test statistic. And then the p-value you would either get out of technology or a table. Here's if you were to look it up in a table, you would see that a z of negative 3.49 puts you way down here and has a very, very small amount of area to the left of it. Here is your critical value, right? Not test statistic. This is your test statistic. This is the critical value, the thing that you compare it to if you're doing the critical value method. If you're doing the p-value method, and then of course you compare your p-value to alpha. But in both cases you can see that when we move on to step 4 to make our decision, we would reject, right? Because the p-value is less than alpha, and because if we were doing the critical value, it was smaller, right? Than the our test statistic was smaller than the critical value, which put it in the rejection region. Both of those tell us to reject the null in favor of the alternative. So that means we're supporting the alternative hypothesis, and the alternative, remember, was our claim. So that means that we have sufficient evidence, right? Step 5, we put it in normal wording. We have sufficient evidence to support the claim that people with money in large denominations are less likely to spend that money relative to people with money in smaller denominations, right? People with change are more likely to spend it than people who have large bills. It should be noted that the subjects were all undergraduates, and care should be taken before generalizing the results to the general population, right? So even though our sample was a random sample, it was a random sample of undergraduate college students, which those people obviously are hugely statistically different than the entire population in general. So you really should only generalize this to to college students. If you wanted to generalize it to the whole population, you would have to run this on a much bigger scale and make sure you got a much more representative sample of the entire population. All right, what about confidence intervals? We can construct confidence intervals very simply, and we can also use confidence intervals, as we've seen before, to test hypotheses, but it's a very bad thing. A lot of people do it, but the number one thing here is that your confidence interval uses standard deviations that are based on estimated values of the population proportion. So we really don't know that those standard deviations of the population are correct. We don't really know that those population proportions are correct. So any of the calculations you get are very suspect. So it's really not a good technique to use. But it's a good technique for just making confidence intervals, right? You just shouldn't use it for hypothesis testing. Let's construct a 90% confidence interval estimate of the difference between these two population proportions, i.e. the people who got $1 versus the people who got 4 quarters. Here's the formula for our margin of error. Very simple, right? We take that, we go plus and minus to the differences in the p hats that we got. That we did p hat 1 and p hat 2, and then add and subtract e to those, and you end up getting this interval here. So that means that based on our statistics, that the difference between those two populations should be somewhere between 0.53 basically and 0.21. The negatives don't matter. The only reason why they're negative is because in this case, the P1 hat minus P2 gave you a negative because more people in the second group ended up spending their money. Now, because this interval does not include 0, it implies that the difference between the two populations would not be 0, right? Because nowhere in this interval is it 0, so we're 90% confident that it's not going to equal 0. But that's a bad way of then saying, therefore, there is a significant difference between the two. It's a weaker argument. It's one that you should avoid. It's better to just run the hypothesis test. If we want to do this in the calculator, it's very simple. You go over to tests, and we're doing a test of 2 proportions, right? 2 proportion z-test. Here's the number of successes from the first group and its sample size. Here's the number of successes and sample size for the second group. We're testing that group 1 proportion is less than group 2. Calculate that, and here is roughly the same answer we got before. The negative 3.49, right, if we round up as our z. And the p here, 2.4 blah blah blah, and then this e to the negative 4, that means it's a scientific notation, so you have to move this 4 times to the left, so you get 3 zeros and then a 2, and that's what we got last time. Same results, a lot easier and quicker. Okay, what if we want to do the confidence intervals? Same menu, only now we just go down to the 2 proportion z interval, right, z int. Our x's and n's are already there. We were calculating a 90% for this one, and There it is, same numbers, right? Negative 0.528 and negative 0.206 if you round up to 3. So very simple in the calculator. Also very simple in StatCrunch. Stat, we're dealing with proportions, right? I know we were doing z's, but that's from when we're dealing with means. Here we're doing proportions. We now have 2 samples with summary because we don't have the raw data. And now we just give it the same information. Number of successes from the first sample out of 46. Then we had 27 out of 43. We want to do a hypothesis test, right? It lets us change this if we wanted to actually test that the difference was equal to something other than 0. And here we're looking for P1 is less than P2, right? Compute. There's our Z, there's our P. Same statistics we got before. If we want to do the confidence intervals, of course, it's the exact same menu. 2 samples, summary, the same numbers, 12, 46, 27, 43. Only now we go to confidence interval, change that to 90, compute, and there we go, the same lower and upper limits we got before. All right, that's how we deal with doing hypothesis testing and confidence intervals for 2 proportions.